Hello everyone, welcome to lecture 11. So we have actually seen what's the meaning of chemical potential in the previous class and how at an atomistic level it makes sense that you don't need to do work or transport heat in the system from system to surrounding, or exchange energy in the form of either work or heat. There is some other way of creating some internal energy or reducing the internal energy of the system, and that is by adding atoms. And the way you are introducing this extra energy is through this term called chemical potential. Okay, so that's the physical meaning of chemical potential. Some of you out there who are also electronics engineers would know that this is how you also define the Fermi level or Fermi energy of an electron, because essentially you are injecting an electron into the Fermi level, right? So how much did the total electronic energy of the system of your material increase? So that is defined as Fermi level or Fermi energy, and so you can interpret it from the definition of chemical potential, where my chemical species now is an electron. I am introducing an extra electron into the system, and the total energy of the system that has increased is by EF. Right. So because I am introducing it at EF, right? So in a metal, for example. Okay. So this is the analogy for the electronics people. If you really so think about chemical potential. What is chemical potential for electrons? Chemical potential turns out to be Fermi level, right? Or Fermi energy. Okay. So in metals, right? So the simplest cases. Okay. Now let's come back. Let's come back to actual chemical species. Electrons we can look at later. So okay, so we have looked at what mu's are, right? So now let us rewrite this equation of so the most important free energy that we have is the Gibbs free energy, right? Because all our growth processes are going to happen in conditions where the important thermodynamic functional that I want to consider is Gibbs free energy. And so if I write dG for an open system, I am going to get dG as VdP minus SdT, right? So I control G by changing either pressure or temperature, or now I can control this by changing the number of species of either 1 or 2, right? Either this is for a 2 component system. N1 dN1 is little addition or infinitesimal addition of atoms 1, right? So you can think of it as just adding 1 atom, right? So that is dN1 equal to 1 atom. dN2 is atom 2. In the previous case we were giving example of platinum palladium, right? Okay, so when I write like this, so then I can actually ask the question, okay, so what is so just very quickly some thermodynamic understanding of what is the volume of the material. The volume of the material is nothing but the differential. So if I change the pressure, how does the G change, right? So the G changes depending on the density or the volume of the material, right? So so this is at constant temperature and at constant N1 and N2, that is the volume, right? Or volume by N gives you the density, volume by mass gives you the density. Okay, so then what is entropy, right? So we did this exercise earlier, dou G by dou T equal to minus S, keeping at constant pressure at constant N1, constant N2, which means this entropy can change if I change the pressure N1 and N2, right? Entropy is dependent on pressure N1 and N2, but at a given pressure, given N1, given N2, entropy is given as dou G by dou T at that pressure N1 and N2, okay? Similarly, what is mu1, right? So mu1 I can also define it now in terms of G. Earlier we were just looking at 0 Kelvin, 0 pressure, and in terms of change in total energy, but now I have a free energy for the system, and that is G. And how does G change? By adding an extra atom, right? So that gives me the mu1, right? So this is sort of analogous to how does internal energy change by adding an extra atom, but this is done at a constant temperature, at a constant pressure, and at a I should only add N1, right? I cannot change both N1 and N2 simultaneously. I should only add N1 or I should only add N2, right? So mu2 will then be dou G by dou N2, right. This is the other way of understanding N1, right. Now, why is this important? Because typically I can control temperature, I can control pressure, right, and I can also control mass flow independently, right. So, in real processes I can control temperature, which is T, control parameters, I can control pressure, I can control the mass flow, by which I can control N1, N2 and so on, right. So, through controllers I have what are called mass flow controllers, I have what are called pressure controllers, I have what are called temperature controllers, the thermocouples, right. So, I have this control system that we spoke about. These are the three parameters that I can control and the obvious potential, right. So, I can independently control them. And so, the obvious thermodynamic potential in any synthesis process then becomes G, okay, even in an open system, right. I can control now the extra control that I have put in compared to a closed system is mass flow. Right. So, mass flow control I can put in number of atoms, I can remove number of atoms, I can put in the mass flow essentially, right. So, that is a controllable parameter, and since that is a controllable parameter, still G for open systems is something that I want to use, okay. Now, you see then how am I typically doing a growth process, right. So, let us give an example of something like called pulsed laser deposition. So, this is a pulsed laser deposition, okay. So, I have a vacuum chamber and this vacuum chamber, so I maintain this vacuum chamber, so on this I have some assembly where I put what is called the target. This is for thin film deposition, right. Then I have some kind of a heater and on this heater I put my substrate, okay. So, there is a base and this base is getting heated resistively, let us say. So, this is a resistive heater. So, I have temperature controls and on this I put my substrate, right. So, on the substrate I have to deposit a film, right, and the way I am going to deposit a film is I am going to shoot a laser, and this laser is a UV laser, right, and this UV laser is going to the first step it is going to do is it is going to ablate the material. Ablate means it is going to create a plasma phase, and this so I want to deposit thin film of barium titanate. So, the target ideally I want to use a target of barium titanate and this target will be some kind of a ceramic of barium titanate, right. So, some bulk material of barium titanate. Okay. So, now I shoot my laser, right, or I shoot argon atoms in high energy argon projectiles in case of sputtering, right. So, it does not matter, and I am creating a plasma phase of barium titanate, a plasma which contains barium, titanium ions, oxygen ions, so all sorts of combinations of this barium, titanium, oxide ions and so on and so forth. So, this plasma consists of all the high energy ions, right. This is process 1, right, or in case of evaporation, right. So, I have to heat the material, heat the target, right. There is always a target that I am going to heat, so that I create vapor phase creation. This is step 1, plasma creation in case of PLD or sputtering, vapor creation in case of evaporation, right, E-beam evaporation or thermal evaporation. Then if I am doing molecular beam epitaxy, I anyway have molecular beams which are like vapor phases. right. So all these are, so physically I already have the sources of vapor, sources of barium titanate vapor or plasma phase, right. So I create them in various different phases. Okay. So this is step 1. Step 1 is creating the phase from which I have to deposit, right. So this is phase 1. Now step 2 is once I have created this plasma, right, again let us go back to the chamber, this is the target, I shoot the laser and then I have created the plasma, this is the plasma, and this plasma then needs to travel, right, it needs to travel in the direction where and then it needs to go and get deposited on the substrate, right. So step 2 is the transport of vapor or plasma, and how you direct this transport, right. So using gas flow, using mass flow controllers, using pressure, etc. So all these control how the plasma shape is, how you are directing the ions or from the target to the substrate. You have to transport material from the target to the substrate either in vapor phase or in plasma phase, right. So these are the crux of what is called PVD deposition. PVD means physical vapor deposition. There is no chemical reactions yet. Okay. So that is step number 2. Now step number 3 is, and this is the most crucial step that we will be spending a lot of time on. We are not going to look at vapor creation, plasma creation, that's going to be part of other courses. We are not going to look at how to actually design your reactors such that the transport is going to happen, transport of this vapor phase is going to happen. That is so that's equally crucial, but we are not going to look at this in this course. You have to take some kind of chemical engineering courses to actually design your reactors, right, such that and the shape of the reactors or so the heat flow and fluid flow problems you have to solve to actually see how to simulate the vapor flow and then vapor flow in a certain way that you want to, right. So typically you say that okay, so if there is a plasma, there is some sort of a cosine theta profile and so on and so forth, but so the important point is you have to be able to transport material from the target to the substrate in a certain way. Okay, so that's what you are doing. So that is step 2. That's also crucial and equally important, and there is a lot of important physics and important vapor transport physics there, right. That we are not going to do in this course, fortunately or unfortunately, right. So fortunately because that reduces the course content, unfortunately because that's also a very crucial part of growth. Okay. But so I'm also telling you the limitations of this course. You are not going to learn that, but what you are going to learn is the third process. Third process, these atoms is going to happen on the substrate, right. Now the substrate is maintained at a constant temperature. The substrate, so the gases that are going to come and hit your substrate are at constant pressure and they are at a constant mass flow rate, right. So the number of atoms that are coming and hitting your substrate are some number per unit time, right. So I have control over these things, right. So these are controllable, right. Now I leave the system like this, right. So the atoms are coming, absorbing, atoms are desorbing, atoms more atoms are coming, adsorbing, right. So I have on the substrate I have to create a plasma if it is PLD, or I have to do plasma if it is sputtering, or a vapor phase if it is something like MBE or evaporation. So I have to do a phase transition from vapor phase to a solid phase, right, and this phase transition is what we are going to look at now. But so eventually, right, so I am starting with such a non-equilibrium configuration, right. Plasma has so high energy plasma and so on and so forth, right. So it has atoms coming at higher kinetic energies, right. So the kinetic energy of these atoms or the species is large. They will come hit on my substrate and then they will undergo what is called thermalization. They will come to the temperature, which means they are coming to thermal equilibrium with the substrate. There is going to be mechanical equilibrium developed, eventually, and there is going to be a chemical equilibrium developed. Now this is very important. Okay, and the way chemical equilibrium is developed, so that is what we are going to look at. That is, so whatever is the G, I want to make dG, so this reaction or this process is going to continue until dG equal to 0, right. It is going to continue until G is reducing, right. So process continues until dG equal to 0, right, or the direction in which it continues is G is reducing as a function of time, right. So G keeps reducing, right, G of the system, G of course is of the system, okay, and it hits an equilibrium. Now at a given temperature, pressure, and so some mass flow rate, the way this goes from here to here, right. So this tells me how, so I can sort of say that this is how, this tells me how the microstructure of the material evolves towards an equilibrium microstructure, right. We said earlier that so if I do this O2 N2 business, right, so argon and hydrogen in a box and I burst this up, then so something is changing. These are the internal constraints, right. Internal constraints are gone. So internal constraints, so the system comes to equilibrium when I have equal concentration of oxygen, nitrogen, argon and hydrogen, right. So system comes to equilibrium in a gas, or ds equal to 0, right, or dg if I am talking about the system with some energy exchange, or df equal to 0 when I have a complete homogenization. Again this means internally I have reorganized, externally I change nothing, right. Now here in my open system also, right, I am maintaining this as P, T and some steady flow of atoms, atom flux is steady. Then when I maintain this, internally the material reorganizes, and that is akin to a reorganization of what is called the microstructure, right. So eventually so with growing thin film, so I said the thin film that I want to grow is barium titanate. So eventually I will get some microstructure where so I have one domain where the where the polarization is pointing up, I have another domain where the polarization is pointing down, I have one domain where it is this way, I have one other domain. So with this domain boundaries, defects and other things, so it will come to one equilibrium microstructure, right, or some kind of metastable microstructure, it does not need to be stable, okay. Now this is what happens, so the growth process happens until it reorganizes and comes to this sort of a microstructure, right. So you can actually start calculating these microstructures. You can do growth in a computer, okay, or so even for closed systems it does not need to be growth. I can say N1 is constant, or so I can go back to a closed system, I can fix it at V and T, right. So in a computer I can fix V and T, right, and I say alright, barium titanate is at a particular V and T, right. So I fix the V and T and I say rearrange the microstructure. Okay, you need to so V and T, but for barium titanate if you are interested in polarization and other things, you should also fix some conditions in terms of the electrostatic energies, right. So that is the electric field or voltage, right. So once I fix all these things and I ask it to reorganize itself, it will so this is the mechanical, this is the thermal, this is the electrostatic boundary conditions. electrostatic conditions, I fix them, and then I ask it to rearrange itself, I will come up with some interesting microstructures, right? And this can be calculated using the purview of what is called phase field modeling. Okay. So, if you talk to Professor Abhik Chaudhary from IIC, if you talk to Professor Panikumar from IIT Madras, all these people are experts in phase field modeling. Professor Shaswata Bhattacharya from IIT Hyderabad, right. So, all these people actually look at the microstructure evolution, but essentially the basic idea of various different processes, materials, it does not matter. So Abhik works on laser induced processes or 3D printing sort of processes, right. So, additive manufacturing, in what is called additive manufacturing. So, what is the eventual microstructure that will come out of my material, because it is not just the structure that determines my properties, it is also the microstructure that determines my properties. The principle is simple thermodynamics. I fix G, I fix T, P, and then I let things reorganize themselves. I let all these internal constraints sort of reorganize themselves, just like the gases have interdiffused into each other, right. Let these domain boundaries form, they move. That is all completely non-equilibrium, but when it goes to an equilibrium, it goes to a certain microstructure, and this microstructure is what determines, so is my final microstructure that determines the properties. Generally, it is not necessary that I have unique microstructures. That is why I have to do numerical simulations of these things, right. So, sometimes it gets stuck in some microstructure that is metastable, right. So, anyway, so this is again slight digression, but so you may want to appreciate that phase field modeling is basically based on understanding microstructures, but based on simple thermodynamic principles, right. G should be minimized. That is what I am doing. Right. So, whatever is contributing to G, let it be electrostatic energy, let it be pressure, volume, pressure, temperature, I have some control variables, that should be minimized, or F should be minimized, does not matter, right. So, depending on what your thermodynamic potential is. Okay. So, that tells me the microstructure, I can actually compute it now in a computer, right. So and it's a very budding buzzing research field, right. So, if I see some microstructures experimentally and I do not understand, I grew this, I got this microstructure, why, right, then I can take help of what is called phase field modeling and do this sort of minimization of thermodynamic free energies as a function of time, right. So, given some initial conditions, that initial condition does not need to be an equilibrium condition, it is like my constraints, hydrogen, argon, that problem, I remove the internal constraints and everything mixes up and then forms these new microstructures. Okay. Alright. So, with that slight digression, let us actually go to any kind of microstructural evolution is what you look at when you are saying that G is changing as a function of time. It is going to more equilibrium microstructures. Okay. Alright. Okay. Now, let us define the idea of what is called a thermodynamic driving force. The one of the most important ideas in this course is what is called a thermodynamic driving force. Driving force to form something, to form one phase from another phase. Let us say I have two phases, alpha and beta. Phases I am going to represent with the Greek letters, right. So, for example, so this can be ice, alpha can be solid phase, beta can be liquid phase, right. Or alpha can be liquid phase, beta can be gas phase, right. So, it does not matter the phases, or alpha can be a crystallographic structure, a BCC structure, beta can be an FCC structure, right. So, phases are different from just the components, right. So, platinum can take an alpha phase or platinum can be in a beta phase, platinum can be solid, platinum can be liquid, right. Platinum palladium alloy can be a solid, which means platinum palladium alloy is in a alpha phase, or platinum palladium can be a liquid, which means the same components are now in a different phase, liquid phase, right. So, the phases I am going to represent it with Greek numerals, the 1s and 2s I am going to introduce, I have already introduced this to represent the components. Okay. So, this is platinum, this is palladium, this is alpha, this is beta, this is solid, this is liquid, right. So, that is the analogy. Okay. Now, and then I said single component system is just N1, this is single component. if I have N1 and N2, then I call it 2 component systems, and in this course we are not going to look at more than 2 component systems. Okay. Now let's so let us start simple. Let us talk about single component systems. I want to make a thin film of platinum. I am just I have a vapor phase of platinum, so I am just adding more and more platinum atoms into my system, right. Okay. Then the only thing, so if I write dg, right, so I have 2 phases, let us say. So the solid phase and the liquid phase. Liquid phase is beta, let us say. How do I change the dg of a solid phase, and I am doing this at, let us say, a constant temperature. I am not changing the temperature, right. The only way then I will change the dg, right, and I am not changing the number of molecules, n is also fixed, right. So it is back to coming to a closed system in some sense, right. So but I want to go towards phase equilibria, so let us come back to closed systems and do this phase equilibria, right. N is fixed, T is fixed, which means when I am changing the external constraints, the only external constraint I can change is pressure, right. I have to do some systematic experiments at constant temperature and constant N. I just want to understand the effect of pressure, right, so on my material, right. So essentially that is the case, right. So the way dg or g of alpha, right, so if my material is in an alpha phase, if my material is in ice phase, right, so if water is in ice phase, then dg of alpha is just given as v dp, right. So I have to V alpha, right. So this is the density or inverse of density. By the way, volume, mass by volume is density, right. And for unit mass I can just consider 1 by V, that is, this is what is called the specific volume, to be the density rho. Okay. So whether I say volume, right, so volume is of course scale with the system, or whether I say density, I am talking about inverse quantities in some sense, okay, with some scaling of course. Okay. Now dg beta is V beta dp. So this has a different volume, this has a different volume, right. So specific volume, let us talk about specific volume. Specific volume is volume per unit atom, okay. So here also volume per unit atom, I am not changing the number of atoms, so volume per unit atom, so I am going to write it as small g alpha, that is g alpha equal to g capital alpha by n alpha, right. So n is the total number of alpha atoms. G beta similarly is g capital beta by n beta. Similarly V alpha is, small v alpha is V capital alpha by n alpha, right. N beta and n alpha are the same because I am not changing n, right. So n number of platinum atoms in alpha phase is the same as number of platinum atoms in beta phase, and I am going to look at these phase transitions. How can an alpha phase transition to beta phase and vice versa, okay. Okay, so specific volume, but in this case, so I am also including, these are not specific volumes. This is called specific free energy. This is called specific volume. And I am not going to talk about specific volumes right now. I am going to introduce that idea later. But just so keep in mind that all these are related. When I say volume of the phase is changing, it means fundamentally the density is different. Liquids have different density compared to solids, right. So I am talking about specific volumes, okay. But so assuming that both phases are, so the number of atoms in both phases are the same, specific volume or the actual volume does not matter, right. So so when I say volume is changing, I mean specific volume or density is changing, okay. So density of these phases are different, okay. Now all right, now let me ask you a question. So I said something of the so something to the effect that V small alpha is larger, right. So one second, let me just check, is that what I said. Alpha is solid, beta is liquid, right. So except for water is an exception, so the density of solids is typically larger than density of liquids. The exception is water, water and ice, right. So, let us not worry too much about water and ice, we will come to the case of water and ice very soon, right. But in general, the densities of solids are larger than densities of liquids. Solids are much more compact, liquids are, they have more free volume, there is enough space for liquid to flow, right. So, as a result, the V of alpha, the specific volume of alpha is less than the specific volume of beta, right. Alpha is the a solid phase, beta is the liquid phase, or alpha is a condensed phase, beta is the non gaseous phase, right. So, then definitely the volume of alpha is less than volume of beta, right. Gas phase has a larger free volume, a larger specific volume compared to the solid phases. Okay. Okay. Now, I am going to ask you a question, right. So, what if I am actually plotting G as a function of pressure, right. The question is, I want to see which phase wins at what pressures. Okay. All right. So, so V of alpha is smaller, right. So, alpha should have, if I am plotting G of alpha, let me plot G of alpha in black, right. So, G of alpha should have a smaller slope, right. So, it is so of course, it can change with pressure, but let us just say that this is the alpha phase, right. Alpha phase has a smaller slope because V of alpha is smaller than V of beta, correct. So, then if I plot beta, the beta phase has a larger slope. A smaller slope curve and a larger slope curve are going to intersect at some point, right. So, this is beta, right. So, this is G of beta, this is G of alpha. Okay. If I ask you the question, at very low pressures what wins? At very low pressures, given a temperature is fixed, number of atoms are fixed in both phases, which phase wins? I am going to say the phase that has lower G, right. So, G of beta is less than G of alpha, so beta wins, which means at this pressure the thermodynamically stable phase is beta phase. Okay. Whereas at high pressures, so beta wins means a high volume phase or a low density phase wins, right. This you sort of know, right. So, I can pressurize materials to form crystals, right. How is diamond formed? Diamond is formed by pressurizing, right. So, these are, so by pressurizing I reduce the volume, specific volume, or increase the density of materials, right. This I sort of know. So, if a material has lower volume, right, by pressurizing it, if a material has if one phase of the material has a lower volume than the other phase, then by pressurizing I can expect that the lower volume phase will win at higher pressures, right. So, at high pressures, it's obvious that lower volume or higher density, right. So, phases will win, and similarly at lower pressures higher volume phases win. Okay. All right. So, that is essentially what is here, right. So, this is G beta and this is G alpha. G alpha is like my solid phase. Solid phase is much stable at higher pressures, P versus G. Okay. So, now I have a rule, right. So, if G alpha is less than G beta, alpha wins. If G beta is less than G alpha, then beta wins. So, these are the thermodynamic rules, right. When is G alpha equal to G beta? That is this. That is where I have an equilibrium, a chemical equilibrium between alpha and beta. nothing wins. This is my equilibrium point. Okay. So, at equilibrium, if I am looking at delta G, so if I am I want to do a reaction now. So, I am going to write this as a chemical reaction, and this chemical reaction is alpha goes to beta, right. This is a simple chemical reaction. So, I am going to define the delta G of this reaction as G beta minus G alpha, okay. And when delta G equal to 0, I say that this reaction is in equilibrium. I am looking at phase transition, but I can still write it as a chemical reaction, right. So, any phase transition I can write it as a nice chemical reaction, right. So, in this case I am writing it as alpha goes to beta. So, G alpha is delta G is G beta minus G alpha, okay. So, when delta G equal to 0, the reaction is in equilibrium, right. Now, okay, so let us again go back to this picture of G, this is alpha, alpha has lower volume and this is G beta, okay. So, this is P, this is T, this is G, this is P, right. Now, I want to find delta G at some other pressure which is not the at equilibrium delta G is 0, right. I want to find delta G is this number, right, at some other pressure, right. So, at a pressure P, and that is equal to delta G, right. So, I can Taylor expand it about the equilibrium, right. So, this pressure is slightly away from equilibrium. So, at the equilibrium pressure which is P equilibrium, right, plus so the Taylor expansion means I go to the first derivative delta G by dP, right, d delta G by dP at P equilibrium again times delta P, so times P minus P equilibrium. Okay. So, this is just a simple Taylor expansion. Okay. Now, what is delta Gp at equilibrium? Delta Gp at equilibrium, this term is 0. So, delta G at a pressure P, right, delta G at equilibrium is 0, it is the difference between G beta and G alpha, right, that is my delta G. So, I am calculating this difference, right, at a different pressure, right, that is just d delta G by dP at P equilibrium times P minus P equilibrium. When I take the system slightly away from equilibrium, this is what my delta Gp is, okay. Now, what is that? Delta G at this pressure P, and delta G again, remember that this is for the reaction alpha going to beta, right. So, that is at the back of my mind, okay. So, the reaction that I am writing is alpha goes to beta, okay, which means I am starting with alpha, will I be able to stabilize a beta phase, right. So, what is this number? What is delta G by delta P? Delta G by delta P is volume of the beta phase minus volume of the alpha phase, dG by dP for alpha for beta minus Vg by dG by dP of alpha, right. So, times P minus P equilibrium, and this volume can be estimated at the phase transition at P equilibrium, right. Okay. So, now I know that V beta at this pressure, right. So, at this pressure, this is pressure P1, let us say P1, okay. So, everywhere I am going to write P1. So, V beta is greater than V alpha at P1. No, I am sorry. So, V beta is in general greater than V alpha, right. So, not necessarily only at P1, but V beta is greater than V alpha, and that is just by virtue of beta being a more voluminous phase, right. So, beta being a less dense, more voluminous phase, right. So, this is like a gas phase, or so gas phase for example, right. And then so alpha is a more dense, less voluminous phase, okay. Now, at P equal to P1, delta Gp is equal to some positive number, this is V beta minus V alpha, this is a positive number, times P1 minus P equilibrium. Now P1 minus P equilibrium is also positive, right. So I have a delta G P, I have evaluated it, that delta G P is greater than 0. Okay. If delta G P is greater than 0, when delta G equal to 0, my reaction is in equilibrium. When delta G P is greater than 0, when delta G is greater than 0, my reaction proceeds backwards. In the sense alpha gives rise to beta, when if I already have alpha phase, nothing is going to happen, right, at this pressure, at high pressure, that is what this says, right. So at high pressure the alpha phase is stable, right. So at high pressure the alpha phase is stable at high pressure. So if I already have alpha, alpha does not go to beta, that is not spontaneous. So this is not spontaneous. So what is spontaneous is beta goes to alpha, this is the spontaneous reaction. So if I already have I have increased the pressure so much that I already have a gas phase, which is the more voluminous phase, then I can compress it into an alpha phase, right. So for example, I can compress a gas phase or I can compress an amorphous phase. What is the amorphous phase? Amorphous phase typically has larger volumes. This is a disordered phase, and disordered phase of carbon is what? This is coal. By applying pressure, I can convert coal into diamond, right. So coal to diamond, coal has larger volume or less density, diamond has more density or smaller volume, right. I can do this reaction by pressurizing, right. So I apply gigapascals of pressure, or so this is what you have in geology, right. So there is immense amount of pressure on coal, that coal you can extract diamond from these regions in Africa and things like that, right. So so diamond naturally forms, but that is because of immense pressure, right. So that's a pressure induced phase transition from coal to diamond, right. So because of huge pressure, of tens of gigapascals or hundreds of gigapascals, I do not know how much it is, but huge consistent pressure, coal transforms to diamond. Why? Coal is a small volume phase, diamond is a large volume phase, and beyond a certain pressure the large volume phases are not stable anymore, they should transform to small volume phases. Okay. Then if I want to then do a reverse transformation, right. So I ideally I cannot transform here back to coal, because coal is a metastable state, right. But so I have solid to gas transition, right. So the way I should do this is by reducing the pressure. Then if I reduce the pressure, delta Gp now is equal to V beta minus V alpha times P minus P equilibrium. But if this P now, or P2 is less than P equilibrium, then delta Gp2 is negative, and what I have is the alpha to beta reaction is spontaneous. I will spontaneously, just by reducing pressure, I will spontaneously form a gas, okay, or form a vapor. Okay. So now the question is, how much should I reduce the pressure by, right. So now so this is G, this is P, this is G alpha wins at high pressures, this is G beta, beta wins at low pressures, right. If I am here, okay, alpha and beta are equally thermodynamically so they are at equilibrium. If I go here at this pressure, beta is winning, but okay, if I already start at an alpha phase, at this pressure I already start at an alpha phase, start with alpha, right. Then I want to ask the question, what is the driving force for beta? I know that beta is the beta will win eventually, right, but what is the driving force for alpha to form beta at this pressure, right. So, can I estimate the driving force, and this driving force delta, I am going to write this as script g, is nothing but, so I have for the so I start with alpha, right. So, I am looking at alpha to beta phase transition. So, I am going to define delta g as g beta minus g alpha, right, and this delta g is negative, right. So, g beta is less than g alpha. So, it has to transform to beta phase, and I am going to define a driving force as delta the script g equal to minus small delta g. I want to make the driving force to be positive, right. When delta capital G is positive, the reaction proceeds or the phase transition occurs, right, and delta g I am just going to define it as minus delta g, and this is g beta minus g alpha. Okay. Now, if the pressure is larger or if the pressure is much so this is P equilibrium, if P2 is much less than P equilibrium, right, or so let me define various pressures for you, right. So, this is P2, this is P3 and so on, right. So, P2 less than P equilibrium less than P3, right. At P3 I have a larger driving force, and that driving force is nothing but delta g, which is equal to minus delta small g, right. I just want to make this quantity positive, right. So, I do not want to look at delta g negatives, right. So, because I do not like negative numbers, I just want to make this quantity positive. I make it positive and I call it the driving force for the alpha to beta reaction to occur, right. If the driving force is negative, this reaction is not going to occur. If driving force is positive, this reaction is going to occur. If driving force is more positive, then this reaction is going to occur faster, right. So, the kinetics comes into play when I have a driving force, right. So, if delta g is large positive number, the reaction occurs much faster, right. Now, at equilibrium delta g is 0. When delta g is 0, there is no reaction. Meaning, so if I am in alpha phase, I continue in alpha phase. They say I continue in alpha phase for infinite time, right. So, I need some driving force to undergo alpha to beta phase transition, and that driving force is delta capital G, and that delta capital G is V beta minus V alpha, these are constants, times P minus P equilibrium, P equilibrium minus P, right. So, because delta G sign changes, and this number, this delta P, how far away am I from the equilibrium point, right. So, this is called the under pressure, right. This under pressure tells me how much driving force I have to form a low volume phase, right. So, to form a beta from alpha, to form a gas phase from a solid phase, or to form a liquid phase from a solid phase, or to form, the correct statement is to form a low volume phase from a high volume phase, right. Larger the under pressure, so larger is the driving force, and if larger is the driving force, I form it much quicker. Okay. So, larger driving forces translate to quicker formations, right. So, the rates come in, we are not going to do rates in this part, we are going to do it in the kinetics part, but larger the driving force, quicker is the transition, right. And then you do not have to wait forever for alpha to beta transition to happen, right. So, I am at alpha phase, I come to equilibrium, and from equilibrium I am still reducing the pressure. If I reduce the pressure too much, then I will degas a lot, right. So, this is what happens at very low pressures, my materials start to degas because they are starting to vaporize, right. The gas phase is starting to form, and that is the idea of degassing, right. So, you have to consider this because low pressures would favor degassing, right. So, the lower the pressure I go to UHV, then I am degassing even more from my solids, right. So, that is what thermodynamics would dictate. Okay. So, I have to take care of that. The degassing will in a practical scenario, the degassing will further increase the pressure, right. But so I have to take care of this degassing issue. It could be an issue sometimes, right. So this is just phase equilibrium. Which phase wins? The alpha phase has a G like this, the beta phase has a G which is crossing it. At the crossover point is my equilibrium. Now, if I want the alpha phase to win, I go to high pressures, and at high pressures I need to have over pressure, right. So, for alpha to win, I need large over pressure, and over pressure again this feeds into delta G for beta to transform to alpha, right. So, that is the driving force for beta to transform to alpha is given as large over pressure, and that is P minus P equilibrium. This should be as large as possible for beta to for alpha to instantly form, right, or to form in a very small time scale, right. So, that is where the time scale comes in. I am applying so in case of coal and diamond, right, there are these volcano events, there are earthquakes and other things. So, some coal got buried inside the earth's crust, right. So, there is some amount of pressure that this earth's crust is applying on the coal, right. So, because of some natural events, and then it took about some 5,000 years or 6,000 years for this coal to convert into diamond, right. Now, if only nature could have provided more pressure, it would have converted maybe faster, right. So, the over pressure was such that the coal could convert to diamond in 5,000 years, right. So, that is where the time scales come in. Okay. Alright. So, the idea of driving force depends, so driving force for alpha to beta transition to happen. If I want to form a low volume phase, then the driving force is such that I should have an under pressure. If I want to form a high volume phase, the other way around. If I want to form a high volume phase, the driving force should be such that I have an under pressure, as much under pressure as possible. If I have to form a low volume phase, the driving force should be such that I have over pressure, right. So, the over pressure or under pressure, all these things feed into the driving force. Okay. This is with respect to pressure. In the next class, we will look at temperature, the effect of temperature, and then combine them both, okay, and then put in the mass flow and things like that. Okay. All right. So, with that, let us conclude this class, and I will again meet you in the next class. All right. Thank you.